So, hello everyone. Let's see if you can hear me. We'll check. So, I think this is going to be one of the last lectures that we have together. Just a second. Looking for link. Okay, cool. Yes, thank you for joining. So the idea would be that today we'll look at transformers, large language models, basically, and next week and so on, I will just like post one more video pre-recorded on the reinforcement learning, because that's something important which we will touch a little bit today, but didn't have time to properly go into it. And then keep in mind we have a specific time and date for exam in different locations. I will be there and we will do the exam on the paper, okay? And or maybe if there is equipment, then we can do it online, but only on person. So please follow those dates. And if you cannot make to those dates, then probably you have option to go to other location where the exam will happen at other dates. Oh, sorry. So I hope that the denoising technology works and you don't hear my coughing, because I'm still a little bit sick. Okay, so these are the exams. Then the reinforcement learning. Finally, so finally, the if what we are doing so far it seems interesting to you, next. So starting from February, I think we will start a new course with more mathematical details and like going much deeper into these topics. And if you're interested, then definitely write me an email so that I know and I can join you that course. And also you can work towards some research or academic, commercial research and so on. Just a second. Okay, good. So that's the plan. But today, let's jump into the very important topic of transformers and generative pre-trained transformer architectures. But before that, the first previous homework, and I saw quite a lot of people submitting the previous homework. I hope that there is not that situation which I explained last time, where there are consistently some students that I think they're foreign students that basically do not listen lectures at all and just generate homeworks. And so basically those probably will get, not probably, I will just give them 0 points, because it's immediately you see that there's no sense in those homeworks. So sorry for those, but otherwise I see some that are really good, and let's look at those a little bit. So let's look into some of these works. So we had to implement LSTM, and or like the best case would be if you use your own LSTM cell function. If you're not able to implement it, then use the implemented one in the PyTorch. By the way, I saw that there were quite a few, at least I saw 2 people, maybe there's even more, there should be more, that are now capable at this moment to implement these functions themselves. So that's a really nice, so already 90% of people are not able to do this. So great for you that you're able to do this. And then later, if you're able to implement such a simple equations and things, algorithms and so on at this moment with these models, you probably, if you work a little bit more, you would be able to implement also much more complicated research and do even, beyond what's already been done. So specifically, if you can do this, encourage you to keep learning this and do some good things. Sorry, hopefully my denoiser works. Okay. So this is the homework. Then the implementations. I saw a couple of them with the screenshots, which is very nice. So let me open some of those. because probably will not be able to train models right now on spot, but it's very easy to see if the work is being done properly or generated. So like if you're a professional, then you can definitely generate code and I would not notice it, but unprofessionally generated code is super easy to see. So so this was one submission, and what is there? Let's zoom in. Can I zoom in? Okay, cool. Okay, it's hard to see there. What are those lines? Okay, let's see. There's one more. There's an implementation just on. Okay, we see that there's lots of repeated words. So one reason why might that happen is because of the weights of the tokens. If you have like words that are less common and then more common, and then you emphasize those which are less common to be more present, or maybe actually most likely this would happen because you did not train it properly on GPU we have this limitation, right, of how many samples. And then here I think this was really nice. So somebody implemented and saved the weights and then entered the sentence here. I want, and then I want at saying has. So it seems about at least logical direction of the sentence structure, which seems really nice. Okay, let's look in the code a little bit. Okay, so let's look first. There's the person who submitted these things actually submitted the built-in version, and then also the self-made version. Okay, so let's look at both. So the built-in version, again, this part, if you don't train it on GPU, then basically you have only 200 sentences. That's specifically done so that you can debug your code. As soon as you're ready to train it, then basically you use it GPU probably, because it take very long time to run it on CPU. So then max len. What about max len? Right. Okay. Yeah. Here. Sorry. Hopefully my cough will go down. Okay. Here. So the embedding. Right. So there's the embedding part. There's a lot of documentation here. Really nice. I have seen generated documentation. I'm pretty sure this is not generated documentation. So really thank you for that. Again, like if you I fully support generative code. It's just that when you learn code, you definitely don't want to generate code, and don't be a wise guy. I can see basically that the even comments are generated. It's super easy to see. So embeddings, LSTM, and then here you actually have number of layers. So the previously and in the homework we had just the cell, and I told you last time that if you basically what you can do, just for you to know, so you can actually do something like this, torch, and then most likely sequential would work here, but if not, then module list, and then you can just write torch and LSTM cell and fill the parameters, right? And if basically that's the same thing like that. So this would be multi-layer LSTM, RNN, GARU, and so on. It's just like written in that way. So okay, let's look down. Again, we need to pack it. So the packing, that's why also it works great with default. Again, I tell this every time, and every time you don't listen to me about this, but hopefully someday, maybe someday, if you want to keep working with me with research or keep learning. So please don't do this. Like it is super confusing. At this small piece of code, very easy. Later you will have problems. Forward. So, and so basically don't use call operator. Basically This just makes it look like a function call, and you will have a lot of problems later. Sure. Okay, so that's just one comment from my side. Maybe we'll have some more comments. And by the way, if you have any questions so far, type in the chat. Okay, so yeah, so that's that. Let's keep digging in. So softmax at the end, right? Here so the predictions. So this is the super important part. I talked. Whoa, what happened? I talked about this last time. Just again a little reminder, and this is something we already talked about it in the classification lectures in very beginning, but I still see a lot of people not doing this properly in many cases, so that you have some kind of weight or coefficient to your cross entropy to deal with situation when the basically. So let me find some example from last time when the words, the tokens, are not in the balance, and this is normal because in any language, natural language, the words are not in balance. So what I mean by that, let me show you. So here, and this is the link to Figma, right? Figma Jam. You can zoom in and look in the. I usually do the like slides like that, right? So here is the one example. The words which have very little meaning, which are kind of not important at all, like the and so on, right? They are exponentially more common in data sets. And if we tokenize it, these tokens will also be much more common. And how to deal with this is that we add this weight value for these words so that this is, so just to visually give you the idea, so let's make it larger. So the weight coefficient of dev would be something along lines, let's say 0.1, right? And then weight coefficient for word Democrats or country, let's say country country would be, which is much more meaningful word, but rare, not as often seen in the dataset. So then probably will be something like within a couple of magnitudes higher value like that. And this is the way how you make sure that basically your outputs are not like and so on, right? Because it will just keep most likely output, right? So that's what we're doing there. Great. What else? So here is the inference part. The inference part, the tricky thing is here that we have hidden vector, which is our memory. So this hidden vector is the whole past memory of the whole sentence that we are modeling. And the super important part is here that basically what we are doing, we are predicting the next word based just on the last word here. So let me think if we could do this just from the memory itself. So the inputs goes in there, H. So I believe like in most cases, the proper way would be just to feed in the last word. We could feed in the like the whole sentence, for example. We could feed in like that till the basically till the end, right? So this would be something like this line to sentence, right? But if we do that, then the memory is kind of useless because it holds the previous state in these kind of embedding formats, and we don't need to refeed all of the words before, right? So that's that. Okay, so this was kind of really nice implementation. Let's look at manual implementation. I think the person submitted that as well. I liked also that the person submitted sorry. Hopefully I will be able to speak. Submitted also the code to save the best weights. So here is the and even this goes beyond what I asked. So there's RNN, GRU, LSTM. Oh, by the way, if you want some golden nugget, I can give you something. Especially this person seems really kind of advanced in this topic, so I'm happy about that. Especially if this person or somebody else want to do research with me, and like thesis and so on, definitely reach out to me. So phased LSTM. So this is I think it was by ETH Zurich. Let me show you. Yeah, it is. So let me give you some next step. If somebody is interested in researching something more about LSTMs, we will just look in a second how the architecture looks like, but the next step would be phased LSTM, and then there is another one which I will give you. So this is for in the Europe, the top university for AI is this one. But in America, that would be Stanford most likely. So okay, so these ones, and let me show you what they are. Hopefully there is something. So there is a simple LSTM cell, and then this one. And this one is really interesting because I think this picture speaks about it. So what you do, you make gates, which are not just sigmoid gates, right? Sigmoid gates means so you have like fully open information gate or fully closed, right? Or something in between. But there is like this frequency, basically. It gives the frequency that some gates are like very like with this frequency, like it's a high frequency on every steps, right, in the time, and some gates are lagging with long time intervals. And if you add this frequency function inside your gates, you can imagine that you can like do crazy things. You can extend your memory like significantly. Here are some great examples. Like you see, there is the LSTM, right, the blue one, and then if you add batch norms on LSTM, I think that also is something that probably you should do. But and then it goes better, right? The higher accuracy for long sequences, but then phased LSTM, it's like really great for long sequences. And also for other tasks, like I think this was language modeling, you can see like it's a huge difference from the simple LSTM. So that's that. I just want to share you one more thing. Uh, There is one more architecture which is really good. Let me quickly pull up something. Um, okay, we'll try to find it a little bit later. Let's go back to the code. Okay, so I just saw that all those hyperparameters assume that the person actually did a quite good job, hopefully. So let's see, GRU units, right? And LSTM unit. Okay, let's look at LSTM. So, well, right. I can also give some comments here, but I like this because there is a clear, clear communication with the equation. So you have all of the parameters clearly defined. There is easier way how to do this, I think. I will show you. So, and then there is the hidden and cell. So these are the memory for the cell. And if you are predicting something based on the previous inputs, you would give these memory vectors from outside of the world, not generate them from zero. So then we do our classical thing where we change the dimensions so that we start with the time steps, and then we have all of the batch dimensions. The one thing which I see the person did not do, and I did not do myself as well, was that remember there is this sequences have now they are not all the same length, so you basically should stop doing the mathematical operations when the sequence group ends, because some of them will have the same length, some will not have the same, but otherwise, let's check the equation. So where's the equation? Okay, so this was here. So, all right. The one thing how you could do this also is that just use linear. So if we see here H and B, or X and B, so these two can be, and usually people actually do it in that way. So the alternative would be just to define some linear layers, like for example for U. So this would be something like self U linear, and there will be torch and a linear layer, and then you just pass the, and the pass inside that basically you will pass in the H vector, and if for some you don't need, then you just write bias false. So and there's also one more thing. Sometimes even people cut out pieces of linear layer so that you would have just one large linear layer. For example, for all of these, you could just write a large linear layer where would be all of the parts f for get gate, input gate, output gate, and so on. And then what you do is, so there will be output and so gate. What you do then next is basically you could pass all of this at once, something like along lines like this, the H, all, and then afterwards you could, so this would be H prime, all, and if you need to access, for example, the H, so F, yeah, for the part which is for the forget gate, for example, FT, then you could just like H prime all cut out some. So this is time batch sequence, and then here would be from 0 till hidden size, right? And then cut out the next piece and so on. So basically that's another common technique, just for you to know that sometimes not define parameters separately, but cut the pieces out of the linear layer and then call it just once. So that's one thing. Otherwise, here I like this approach where you write the inner part separately so that you can debug it and test it. Seems very nice. All of these are nice. And then these are the Hammond products, are simple pairwise multiplications. These are also nice. Then the appends, stack. Yeah, I have I think really great work here. So this looks really nice. Let's just pull off one more, and then let's go to today's lecture. Okay, so let's look at one more. Okay, LSTM cell. Also, remember always the biases for all of the tasks are always 0. The weights can be uniform. They can be also normal distribution, Gaussian. They can be all sorts of distributions. So they're usually hyperparameters. You try to find some that works the best for different situations. Even for some models, they specifically say what kind of initialization you should use. Okay, and here is the input, right? Okay, so here the hidden vector is used as the tuple. This is also one way how it is done. I think in the original LSTM implementation also this is a tuple, so we can do that. Then decode it. This is nice. Then permute it, right? Okay, so here is the problem with the matrix multiplication. Again, I think first of all, you definitely can do the matrix multiplications in this way, but this kind of it's a slippery slope, it's very easy to make big problems for you, because the matrix multiplication is actually a two-dimensional algorithm, as we did it in first lecture. So let me explain what's happening here. So with xt, we were talking about specific time step. So this shape will be actually batch comma embedding. Okay, so this will be that shape. And the other shape here for the for get gate, or let's say input gate, w input makes more sense, would be from embedding to hidden, right? So this seems right. So far so good, but the thing is, we can shift it around in the way that the output will be batched by hidden, but this is like kind of mathematically dangerous, because you could just easily end up by mixing in the batch dimension here, batch dimension, right? Because I don't want, so basically what we have different sentences. Imagine there's sentence one, like brown fox jumps across the I don't know, river, whatever. There's other sentence, like there's so the longer sentence, right? There's another sentence, shorter sentence, and so on. So these are different sentences, and we go by each word, right? So, and there's a batch 3 right now, then there's another word, and so on. And we're trying to predict the next word. What we are trying to predict, the word is located here, right? For example, all of the next words here. What we are wanting to do is that we want to predict these words based on the previous words, but just in this one sentence. So if I want to predict this one, I'm based on these two words before in that sentence. Definitely don't want to predict this word based on a word in another sentence. And if you're not careful, you actually are training model to do exactly this, and in this case you actually are doing that. So the correct way how to do this would be something along lines like this. Let me show you. So you would add here, so you would add here an additional dimension 1. Then what you will do is you will basically do the dot product, which is two-dimensional algorithm. It's not a magical operation with these things, and get out as an output. We will have, so this will be out shape. You would have batch comma hidden comma 1, and then you reduce that one, like just like squeeze it, right? So this would be the correct way. So never do that. Always do that basically, and then the output is that, and then it's correct. So it's probably one of the reasons why it didn't work for this person. The results were not as good as for the other person, because the equation was done wrong way. And again, how to do it right way, just for everybody to know. We'll take it from that other work. So this is the right way to use, and this is not the only way how to write it. You can write also and like the torch, expand dimensions and squeeze, but I like it a lot better in this way. It's just cleaner, just much cleaner. And today we're also going to do matrix multiplications. For every single matrix multiplication, always where there is a batch size, you should pay attention about this thing. Okay, let's then just go to the next step. But okay, before that, I just remembered about the weights. Where was the weights for the words? Okay, so here I see it also really nice. So this was the work from that student, which did it quite good. So here there was the yeah, so there was the testing of these words. So the student chose coefficient of 100, smooths it out, right? And 1 is more aggressive, exactly. Like you need to find the coefficient here, which kind of smooths out the vocabulary and makes the so that not only rare words are important, but also not so rare words. But at the same time, it cannot be just these frequent words, right? Okay, so let's jump in today's lecture. Just a second. So this is that. All right. I will one thing before we jump in today's lecture. I will open in the Moodle the template so that you have access. Moodle edit mode. This is not the right course. All right. I remember the courses. We will do the exams, math-based exam and the business exams at the same time. So there might be some people who are working on much simpler tasks, but basically that's a different direction of what they are trying to achieve. Okay. Just a second, I'm pulling up the template. Okay, I don't like this template. Just a second. I'll give the fresh template. AI course, transformers. Where is this template? Compress, share. Okay, template is coming up. Is it? Yep. Just a second. Okay, 12.2 task. And the template and model architecture. Okay, please get the template. I just posted it here. And meanwhile, while you get the template, I will try to look up one more thing I want to share with you. I found it. Yeah, please get the template meanwhile. So the one model which is RNN type of model, which is as good as the transformer model, which I want to show you. So this paper is from 2023, I think. Yeah. So this is kind of really good also paper and model. So this, if you look at the benchmarks in a competitive benchmarks of language models and time series modeling tasks, this one still is up with the large language model with the transformer based architectures, but this is basically RNN type of architecture. So let's try to look here. So right, first of all, of course, based on transformer, which you will see in a moment, transformer is a very hungry model. It is extremely hungry model for resources. That's why we cannot model long sequences. With the RNN models, we actually can model long sequences. And you see this one is kind of like on the par with the other simpler models on the resource side. But then on so this is the kind of architecture, but where is the results? I think there was some kind of table, right? They actually have quite competitive results with regards to transformers, actually. Okay, also these are the question challenges, I think. Right. Right, so they compare with the Bloom, which is also a transformer model, not the state of the art, but in general, it is kind of amazing that you don't use these attention mechanisms here, but you still get the same results as from the transformer models. So this is something to definitely look up. So I showed you the phased LSTM, and the other one is this model. So these two are kind of the very important parts which we did not touch yet. So okay, good. Let's go into the transformers now. So page 3. Okay, let me also check if there's any questions so far. Okay, good. Okay, so we'll not try to make it too boring. Let's try to make the main ideas here, and hopefully you can transfer these ideas on how you use ChatGPT, basically, because what we are going to talk about now, this is the same architecture used in ChatGPT. So the one architecture which I gave you as a task is this one. So basically what happens here, so this is the GPT architecture, and by the way, the GPT architecture has not changed over years much. There's a little bit of changes in like meaningless changes in the layers themselves. I think they basically they don't publish the GPT-4 and GPT 3.5 architectures, but this is GPT-2 architecture. And we can find out what is happening there. So you will see there's significant changes from. So and this is transformer, simple transformer, because the original transformer is actually much more complicated, and this is very different than the recurrent neural networks, even though both models do exactly the same thing as model the language, right? This is a completely different way how it works. So first, the inputs X, right? So the inputs are still the same old task that we did last time. Again, for those of you, to remind you what we're trying to achieve here, let me find some visualization. Maybe this one will work. So we're doing the language modeling. We're doing this. So each X is actually that blue sequence of words, the sentence, and we are trying to get the predicted word. So maybe I can just color code it. So this is the input, X, right? And this is the output, orange, right? And here is the output here, just that one word. Some of the interesting things to notice here is that the embedding matrix, which we know already what it is, right? This is the word embeddings, the proper way how to represent classes and tokens in the mathematical format. You see it here, and here it is the same embedding matrix but transposed. And by the way, the transformers are really thriving, and the transformers one of the main functions is actually transpose. So here weights transposed with the hidden, and the output goes the same dimensionality as the basically one hot encoded vectors. And this is really cool because we are making the embedding matrix much more stronger, so that words not only come as an encoding, but also the same embedding matrix goes as the decoding part. So that's why it's very, very cool. The one thing which is very new, something that never existed before when we talked about things, is this part. So positional embedding. And the way how we will run this will also be very different than how we did it before. So the positional embedding, and this is also fundamental for ChatGPT, even for ChatGPT. So you will know now how to use ChatGPT better. So let's post what is that part. So basically, in most cases, it is pre-computed positional embedding, which signals the position of which the word exists. So, and by the way, you can add positional embeddings to LSTM models as well. It is calculated in this way. You have the the table is calculated in this way, but then you select out of it just these positions. So here in this case, let me see. Right, so there would be, in this case would be, you need read this table in the way that here is the time, right? So this will be the time. And on the y-axis, there will be the positional embedding. And immediately get-go, you need to kind of understand a couple of things. First of all, even for the RNNs, if you feed in the positional embedding for each time step, it actually helps. There is a, I think I shared you last time one link with the tricks and hacks for RNNs, and one of the tricks is actually to pass in which word are you currently located. Basically, that is what this does. And the trick here, the very important trick is this one. Let me show you. So basically, if I have embedding, positional embedding 1, right? So if we are now, let's say, so no fill, okay, cool. Yeah, this will be red. Let's make it a little bit larger. Can we do it larger? No. Okay. Strange that the weight of the line is not available, but right, don't care about that too much. Okay, cool. So yeah, so this will be positional embedding 1, positional embedding 2, word 3, word 4, okay? And then let's say this is word, and this actually it is word 200 something, right? And what I'm trying to illustrate here is something very fundamental, and hopefully you understand it now. So that for the first tokens in your basically your inputs, this is like, see how many informational points there are. Like basically, if you calculate standard deviation here, you would get a significant value, right? For the second word, again, quite significant value. So lot of information there for the first word, for the second word, for the third word. And what happens if we go to 250 word? We see we also get a little bit of information, but even we don't see it even, because the intensity is now basically the same, even if it's like 200 word, or maybe this is like 300 word, right? Any word afterwards will be just like, it doesn't even care that much of the positional embedding. So what I'm trying to say here is that when you use ChatGPT or large language models, the first tokens are much more dense information than the last token. So this is foolish and kind of really not good idea to add in your prompts the more important information at the end. Like actually what you want to do, the first task, right, the first word should be the most important one. So and the worst thing that you can do is actually start your ChatGPT sessions with hello, how are you doing, and things like that. You will just destroy all of your good tokens and feed in all of what you need to do in the bad tokens. So that's one thing to understand what's happening here. And this is just pre-computed matrix where we select things. You could also do learnable embeddings, and probably because people do not use ChatGPT in a proper way, like in the way how the transformers work, I believe that they have done something about it in the GPT 3 and 4 models. I believe that in the 3 and 4 models, they probably don't have this kind of embedding matrix for positional embeddings, but still, this is something to keep in mind. Okay, so that's that part. Let's keep digging in, and then we'll go back to the idea of how all of this actually. Basically, I will go back to the original transformer as well, because this transformer is simple transformer, GPT transformer, the same as in ChatGPT, but this is not the original transformer. will give you a little bit of the history as well. So the middle part. So this was the positional embedding. We already know the word embeddings. We already know what's happening here, the inputs, the outputs, right? The another thing. So the middle part. The middle part is critical. So this part. Let me color code it. That is the critical part. Of course, the colors doesn't work. Let's see. Interesting. Why this circle doesn't work? Right. Let's make it in some kind of okay. Let's do it in blue color. I don't know. Okay, so this will be a blue color. So the middle part here, this is the blue color, and this is basically that here, right? And again, as soon as you see boxes, every box means mathematical operation, okay? The one super interesting thing you already see, there is a softmax in the middle of your architecture. That is something that should pop out immediately, because softmax is normally only at the end of your classification tasks, not something in the middle of architecture, right? So, and what actually that part is. So that part can be visualized in many ways, and there is one link in the notes of the lecture which I also recommend to open and see. So that is illustrated transformer blog post, very popular blog post, where you can go step by step visually how this works. By the way, this what they show is the full transformer from Google. But what we are doing is just this smaller, simpler version. Let me give you the example here as well. So here, is this equation. Okay, so we'll see the main point of what we are trying to cover here. So we have something which is called query, key, and value, right? And how we get query, key, and value, that's also very interesting, and how it behaves is also very interesting. So let me see. Okay, so I think this one is very good. Okay, let's dig in with this one. So we have the inputs, and we have the embeddings, okay? Let's annotate it a little bit more. So thinking machines, and then we want to predict the next word, okay? So what's happening here? So we have these embeddings of words, and actually they are not just embeddings of words, there is actually plus immediately the like the positional embedding. So embedding of position for position 0, and then for position 1, and so on. This is also added immediately. By the way, if you remember the UNet lecture, when we talked about the skip connections, one kind of, at least for me, I think always, it seems that here should be concatenation of the X embedding for the position 1, or in this case position 2, with the other one, right? Just concat, right? But if you try to do experiments as exactly as for the units, we find out that the concatenation and plus the addition works the same way. It's just the concatenation takes much more resources. That's why nobody do it in this way. Everybody actually do, instead of doing concatenation, do the just adding, mathematical adding. Okay, so this so far so good. So far I think everybody follows. Then happens the very interesting part. So what we do, we take the dot product. Here's the 4 by 3, right? So this is the, basically, as we could see, embedding dimension, and then this would be hidden dimension, okay? And we just do the linear layers. So 3 linear layers with exactly the same inputs, basically. So we take as the input this thinking word with positional embedding 0, and we get out this one. Then we take as an input machines, and with the positional embedding 1, and we get that one. Maybe I should just write it 1 so that there is no confusion here. P2, P1 position, okay? We take those as inputs, we get outputs. And basically the other thing is what you need to see here is from the same inputs, from the same embedding inputs, not from different inputs. Exactly the same thing goes here. We get that output, goes here, we get that output. If we start building custom architectures, we definitely can do this, right? We can, in parallel, execute multiple linear layers and get different paths of the neural network output, right? So, and then here from the same embedding, we get out that one. So we got out from using these linear layers. Basically, they are linear layers or just embedding matrix, not embedding matrix, just simple matrix linear layer. So there are actually 3 linear layers, right? So linear layer query, linear layer key, and linear layer value. So we just got from these out the actual. We feed it in the same input 3 times and got 3 outputs for each word. The one thing we already see so far is that so far we don't see any kind of memory like in RNN cells. Nothing flows from the previous steps so far, just everything happens in parallel. So this is already making this model much more faster than RNN because we can just feed in everything in parallel. We don't need to feed in the previous time step to get the new time step so far. So far, so good. The one more thing which I want to highlight is that there is a query key value, right? And this is specifically built in the way so that people imagine that there is some kind of values, then there is some kind of request, some query, and the request is executed on keys. So we're searching for something based on keys in the values. The one thing which I still don't see a lot of research in that, but probably it's because it doesn't work. But the thing is that you could theoretically, what you could do is just take for example, this stuff directly as a value. If the dimensionality is the same, nobody stops you from doing that. You can also change that keys are something predefined. So something like that also can be done. By the way, I have seen, I think last year, quite a few attempts to get rid of the matrix multiplications you will see in a second in that way, to try to do the keys using some kind of pairwise distances. So this is how we get from the very beginning these 3 vectors, and then we feed in those 3 vectors inside this function. And here specifically, this is again done on purpose. You see there is not only just 3-dimensional vectors, but these are actually for both words, thinking machines. So let's color code it again. So here, this is the word thinking, okay? Here it goes again, thinking, right? And then machines will be, let's color code it with violet. So machines is here, machines is here, machines is here, and the interesting thing is machines is also here. We're trying to predict machines here now, and then the next word, so we're trying to, when the word is thinking, we're trying to predict the word machines, right? And then from the machines, we're trying to predict the next word, which is not here visually well listed. So let me just add here a note. Trying to predict machines word, machines, and then the next word is actually after machines, after next so trying predict word word after machines. Okay. Okay, cool. So the first one was trying to predict machines and then trying to predict word after machines. Okay, so that's that. So here is the salt. This is actually the heart of the whole transformer architecture on all of these architectures. This is the essence. So basically, this is the heart. So just for you to remember. So this is the essence of everything. And what is the essence of everything actually is the transpose operator, transpose here, because specifically color-coded things here, try to explain you here, because previously everything was linked together with the hidden state, with the for loop, with the previous basically memory of the what was generated, and with the transformers everything changes. What happens is that we are transposing keys and we are basically leaving queries like that. We are applying softmax, which is basically saying that give me one token to focus on and copying from values. And what is the output of that function? So the output of that function is something significantly important, and this is the attention matrix, the output basically. So it gives as the output the attention matrix. Let me just see if everything is correct here. Okay, yeah, so I will color code exactly which part it gives you attention matrix, because not everything here gives you that. So let's use the, again, green one. Okay, so this part, softmax part, is exactly this one. So why is that? Again, the two-dimensional matrix operations dot product. By the way, here should not be the sign. There should be dot sign, basically. So this is the at sign, at sign. This is the dot product 100%. And visually, what's happening here is this. I have two dimensions here. I have two dimensions here, right? These I remove. And now I have 3x3 matrix, just 3x3 matrix. And this 3x3 matrix, and in this case, this is a little bit more matrix, right? The more words gives me the attention to all of the words in the sentence, either ahead or before. And in the many cases, what people do is actually we try to black out this part so that the transformer cannot see the future. But in some cases, you want to see the future. For example, if you do the translation task, in translation, some languages have different order of words, so you might want to see the future. But for language modeling tasks, you definitely don't want to see future. So how this works? So if you have words, so the prepare word, right? Prepare extract, right? So this would be the, let me see, so this would be the first word. Let me try to help you to read this. Maybe also I need to remove a little bit of these annotations, otherwise you cannot see anything here. Okay, so let's try to read this this attention matrix, and we can build these attention matrices later as well. So this will be the word 1, right? So this is the T1. There will be time, and I don't like actually how it's written here, the attention, because it doesn't make much sense, at least I think. Right, prepare, extract. No, it is correct, sorry. The time is on this part, so time, and this will be the attention. Yes, exactly, attention. So the first word goes in, so this is the T1. T1. It don't see the future. It means that the only attention is to itself. So the T2 pays attention to the prepare and extract. Again, that's the same. So we go down to the next word and so on. And if we go to the word now and, so word and, which is here, and, right? it pays. So when I'm located here, I'm paying attention to this word, actually, extract. And if I'm using the softmax, it will pay attention mainly to just one word. That's why we need to have these, basically that is one of the reasons why we need to do this multi-head attention, so that we don't just pay attention to one word, but to some multiple words. So there is a hyperparameter of how many these self-attention layers we want. And one thing also for the ChatGPT, so I showed you the importance of first tokens. The other thing is here, what we see is just from the equation, we get attention to some specific one word. And then what we do, we copy that word to the output. So that is also something to keep in mind. The ChatGPT works by copying the inputs to the outputs very well. Of course, it can change the inputs to the outputs in different manner, and that's why this model is so powerful, that it's not only capable just to copying things, but also to generating things, right? But the copying part is built in the equation. Okay, so that's that part. What else? What else? So that is that part. Maybe some visualizations more. Let me see if I have something. Sorry. Oh, right, I think these are good. I have actually full equation for this. Let me look at the full equation for the transformer model. So this would look like this shift. Okay, so this would be the full equation. So if we go step by step through this, okay, so that's that part. So we have the X, the inputs. We get out these query key value vectors. We do the transpose here. We get the attention. And the actual model goes here. So this is n times n blocks, right? So we get the word embedding, positional embedding, put it into the attention, have the skip connection here, which is we still get these skip connections everywhere, which is definitely something that will change in the future. The skip connections is not it's not really kind of the best way to encode information. Is just to hack to avoid the vanishing gradient. Then the layer norm, by the way, is something that has been proven often to be very good for RNN models as well. So this is similar to the batch norm. Let me just show you some example how layer norm is different. So this is again mean, standard deviation, and so on. So that is simple part, but the interesting part is something else. Let me show you. So layer norm versus batch norm versus instance norm versus group norm. It just depends on which dimensionality you use. So here's another image of that. Right. So and the kind of standard version where you cannot go wrong. So the kind of the default version for normalization would be batch norm. And you remember the normalization is super important, because otherwise we will get dead neurons, right? And here actually we have a ReLU function, you see? ReLU, right? And if there is a ReLU, it's very easy to get dead neurons. We don't want to get dead neurons in the feed forward network here. So yeah, so the batch norm. So there is how to read this. So we have feature vector, channels vector, and batch vector, right? So batch dimension. So and then what it means is for each channel, each channel, basically we have separate batch normalization. In case of, by the way, in case of one-dimensional batch norm, then we just don't have that. So I would say basically this is the feature dimension, and this is the batch dimension, and the channels is just because we have multiple dimensions in image dataset here. So, and then for the layer, this is interesting. For layer, for each batch sample, for each sentence, we have separate normalization. So this is based inside the sentence. So basically normalize inside the sentence itself. So that's something. And here it is basically normalize basically each word separately, and then you could have also basically group normalizations. Yeah, so this is in layer normalization idea, but basically, yeah, so the group normalizations is where you cut it in separate pieces, because sometimes the idea here is that maybe sometimes some images with pixels in let's say red color have different normalization than pixels with blue and green colors, for example. Anyway, so these are the normalization functions. The only difference between all of them, even though the equation is the same, is on which direction you calculate the normalization. You could also do probably, let me think if you can do it. Yeah, so basically if you do the normalization in every direction, then that's an instance normalization. If you just take from all of the pieces. Okay, so that's that. Hopefully it's at least clear in that direction. Okay, let me give you a little bit, before we start coding this task, let me give you a little bit of background on how all of these things happened step by step, and then we will code it. Again, just to keep you informed here, if you go back to the original architecture here, so this is the attention layer, right? Everything here is very simple, just the simple attention layer here, which is this transpose operation, right? So why this works, again, keep reminding you, it's because in the attention vector we have, so basically transpose on sequence dimension, basically, and that's why we get attention matrix, and that's why we are able to do everything in parallel. So what it means is, so some of the very cool features for transformer is you can do, so first, good features, okay? So one is train in parallel, like convolutional networks, train in parallel. Basically, no for loop in training. It is not the case in inference. When I want to generate stuff, I don't see the future. I don't know what is in the future. I would not be able to generate in parallel without for loop. So for inference, I need for loop. So train in parallel, no loop in training, for loop in training, that's a powerful thing. Then what else? What else we have a good thing? So basically high quality results, and then the bad features, so one, very high memory consumption. So basically the so it is the sequence squared. Everything is sequence squared because we are trying to do this operation, right? The dot product in between the transpose. So, and this limits the length. So strong limitation on length. Strong. And how they deal it with this nowadays. So in the modern architectures, they actually, if you see that is cloud with 100k tokens, so how they do it is they're cheating it. They're not using the full transformer. They're mixing it together with recurrent models, basically. So then if you're mixing it with recurrent models, you can get away with longer sequences, but the quality will be much lower, actually. So that's one thing. So if you want to get the best results, keep your sentences short. Basically, that's also very important. Then also no memory, no memory at all. Just attention for based on inputs. So all of the memory that is existing there is just based on the training memory. You cannot add basically some kind of memory during the inference, except you can give more context, more tokens of value, and hope that the outputs will be copied basically. So that is some of the bad features for the transformers. But then the history, how it goes. Let me see. Okay, so maybe I can just post it in the another page. So let me show you. So there are I think like let me show. So 1, 2, 3, 4, more or less 5 steps of how to get from this to the ChatGPT. So let me write it down, and you'll see how fast you get there. So we actually got there really fast. So I'll give you these links. You can study them yourself. I will explain a little bit how this happened and what is important about these things. So, okay, need to clean it up a little bit. So these are five, actually 4 steps, more or less, 4 to 5 steps to ChatGPT. Steps to ChatGPT. ChatGPT 4 plus, right? So anyway, so you see everything started in 2017 with the Google transformer architecture, which I will show you in a second, which is different from the simple OpenAI architecture. And the Google transformer architecture, probably, I'm not really sure if they actually use it in the Gemini model, because I believe probably they just opted for OpenAI architecture themselves. Nobody tells really what kind of architecture is everybody using nowadays, because everybody is actually a little bit scared from each other. You'll see in a second why. So so these are the most significant papers in the order and the years. So 2017, this is Attention is All You Need paper. And this introduces the transpose equation basically. So, and the funny thing you see already here, like for many years, like so original year 2017, now we'll have 2025, so 8 years ago. So for many years there were not this kind of disclaimer. Like only when Microsoft invested $11 billion in OpenAI, the Google added this disclaimer, provided Google hereby grants permission solely for journalistic and scholarly works. So they basically had this kind of, the Google management understood that all of the world of AI has gone ahead of them, like because OpenAI got better models than Google. Many search engines arose like Perplexity and others. Basically, even ChatGPT search nowadays is better than Google. And Google just then said that, okay, we invented this, we didn't want you to outsmart us, right? But so the original architecture looks like this. The first part is exactly the same as our model. The second part is more complicated. They have these lines in the middle, which are the hidden connections inside the middle of the model, and the outputs are actually generated from different paths, so that inputs goes in here, but the outputs at the same time goes from the other path in, also with positional embeddings, and then on top there is the probabilities. So it's not an it is actually autoregressive model, but it is more complicated model because you have 2 paths for the inputs, right? This is for the inputs and then for the outputs as well. So this model probably is better for translation tasks when you need to translate something on different length sequences, right? one language you have shorter sentences, another language longer sentences. This might be better, but this is much more complicated architecture. And initially, when they did this, they had great results, and basically it was the first kind of model where you can train time series models in parallel, which is great. So this is one. Next one was first GPT model by Ilya Schulister, which is the super popular person nowadays who left OpenAI recently because of their arguments there. So here are some of these authors. This is the first GPT publication, and in their publication they also show that what you can do, you can train this GPT model and change heads. You can change heads for the classification, for the similarity search, for the multiple choice questions, and so on. But this was still not the way how we do things nowadays. This is actually more precise way to do things. If you need to have the classifier, better do it in this way than using the prompt engineering. So that was the next one. So then the first paper actually on the prompt engineering beginnings was from 2020. So this is 5 years ago, basically. 5 years ago, the first prompt engineering paper, language models are few-shot learners, and the prompt engineering nowadays works the same way still. Let me show you a couple of things here. So first of all, so the more examples you give in the context, the better outputs. So this is exactly what we talked about, that if you have large model, or like 175 billion model, which is extremely large model for nowadays. Nowadays, actually, everybody is working on about 8 billion models and getting much better results. So, and what you get here, and this is like, very important actually, you get here 0 shot, a 1 shot, and few shot learning, and this is based on prompting. So this is not based, like I showed you before, on OpenAI paper with the classification heads, but you're just having the language model, simple language model, and you're trying to do language model things which was not built for that. So, and if you just ask to translate sentence just from get-go, you get very low quality translation. If you give one example, you already get about 50% precise translation. And then if you add more translation examples, you can get even 60 and plus. And this is the same way how language models works nowadays, actually. Many people still don't realize it, and it's very hard to explain because you will see in a second why it is hard to explain. Okay, so that is that, and how it in reality looks like this actually. So 0 shot, translate English to French, cheese, and I want translation. And if I do this, I will get very low quality. If I say translate English to French and give one example, nothing to deal with cheese, about like peppermints, giraffes, whatever, no, nothing to deal about cheese, I will get 50% accuracy. And if I give more examples, I will get even higher percent accuracy. So this is the trick being used nowadays for all of the prompt engineering, and many people kind of don't realize this and try to do some kind of magic prompts, basically. So just to explain more about this is that if you go and look for benchmarks, so let me try to find some benchmark. For GPT, for example. So like most of the benchmarks actually also used n-shot learning. Let me try to find some examples. It's not actually learning. It's basically just n-shot method, and you will see in a second how kind of foolish is often people basically don't know what they are looking at. So here is Cloud 3 benchmarks, and the one thing which you definitely need to pay attention is not the high superhuman accuracy, but this number, 5 shots. So 3 shots, then let's say 8 shots, see? Like 5 shots or whatever, like, or 3 shots here, even chain of thought shots, which is even more hacky way. So all of these 0 shots are great. Actually, 0 shots means that these are like proper models actually. So as soon as you start doing this 5-shot thing, this is like fishy territory, because you're doing this basically. When you are trying to get your results, you are trying to get results in a way that no human person ever tried to get in that way. So basically, you're randomly selecting samples of the same dataset, putting them into the prompt, so you get better output. And this actually works, and this is the proper way how to do things, is to copy a lot of information in the transformer so that you get best results outputs. Okay, so I don't want to stick too much in the history. I want to do also coding today with you. So, but this is important point about all of these models and how they are kind of fine tweaked so that it looks like they are superhuman. So that's one thing. Then the next thing, in 2022. So this is 2022. So this is just 3 years ago. Basically, GPT 3.5 and so on. The secret sauce for GPT 3.5 and so on is actually this thing. So this is the what is the name? So first of all, it was based on supervised fine-tuning initially. So you have pairs of the inputs and outputs, right? So people ask questions and what is the right output. And then later they change it to this way, to reinforcement learning from human feedback. And then you need less shots basically. And this way is this way basically. So you have, let me show you. Oh, right. I cannot zoom it more, but let's explain this thing, how it works. Hopefully I will get it right. Right, so this is actually SFT. I think this is not what I want. There should be some other diagram. Let me try to find. Oh no, it is the same diagram. Okay, cool. So how the model becomes more human-like rather than just like this normal language model. So you have explain moon landing to the 6-year-old, yeah. Then there is the response of the labeler, human labeler response, right? And then you have this first model which you train, but this model what you train actually is not generating the output, but it's generating the reward. So the y prim is the reward. So it gives basically the quality score. Basically, it gives the quality score. You train simple regression model to have the inputs of so the inputs are actually both things, the prompt and the human response. And the outputs are actually that humans are labeled what is the quality of the response, right? They give the score from 1 to 10. So this is good response, this is bad response. So you train such a model, and this is your reward model. And that's why I'm saying that today I'm touching reinforcement learning a little bit, because reinforcement learning is something which is very important. So this is reward model. And then when you have this reward model trained, you can use this reward model to basically put it inside the training process of generating any kind of responses from any kind of prompt. So you can generate all sorts of prompts that you want, the same prompt here or any other prompt, and you will get some kind of generated text. So here's some 4 versions of generated texts. You evaluate it using your pre-trained reward model here, and you then train your model on the sequence which gives the highest reward, basically in this case B sequence. And in this way, you can imagine how powerful it is. You can generate any kind of prompts you want or collect it from your datasets and then generate the outputs many times, like hundreds of times, and then use reward model, which is pre-trained already, to evaluate which output is the best output, and your language model becomes more human-like, basically. So this is the second step here. So this is how we get from what I showed you in the previous slide to the ChatGPT. And then the last thing is, there are attempts in 2023 and even attempts going on nowadays. This is open research topic. This is from Stanford, for example, to try to change this process so that we don't have this reward model for policy making. We would have direct kind of model. But again, I don't think that this is the complete answer, because this way is definitely not better than previous way. It's just that it is easier to train it in this way. But still, there is no clear answer how to train it the best. This something will happen probably in coming years. Okay, so let's go to the code now. So I've been talking a lot. Hopefully you already got the template. Oh man, how can I? Okay, let me try to get. Oh no, like that. New page. Okay, so this will be the coding page. If you don't know, you can switch pages here. Okay. Okay. So let's go to my template. So this will be my transformer template. I will go quite quickly because we need to wrap up by 6. So then you can catch up a little bit later. If you have any questions while I'm coding and you observing, write in the chat. If any questions so far, also write in the chat. Okay, so no questions so far, at least I don't see them. Right. Hopefully you get my point about how these technologies arise, right, and where we are right now. Still a lot of research topics to do, so this is not a finished thing. To you can still do a lot of great stuff in this field. Again, because of the bad things, I showed you the bad things, right, about the basically the bad things about the memory and other things, right? So the memory problems, we still have huge memory problems with transformers, and how to train them to be more like human, so that we don't need to put in these end shots and so on. Okay, so let's go. So there is a quote dataset, the padding, these things. So there is a positional embedding already given to you with all these sine cosine functions with those which I showed you. Right, seems a bit bad. All right, so this is not something that I wanted to show you. Something weird. Okay, let me try to find again. Okay, so maybe I opened the wrong file. Okay, so the positional embedding is given. Okay, the transformer layer. Transformer layer is the most important one, which I want to go step by step through with you, so that I don't mess up this, so that you also understand how this works. So, okay. Again, I will give some comments along the way while coding. So there will be feed-forward models for each of these or projections. We can call them projections, or they can be even convolutional models. Remember that let me think, can they be convolutional? Theoretically they can be, practically it doesn't make sense. But they can be more than just a linear layer. They can have actually sequential with multiple parts of it, and this would be completely fine. But just in the most basic version, there will be in features, which would be hidden size, and the trick here is that everything is hidden size. Size doesn't change here. If you start changing the size, you will have lots of problems. The input size actually comes from the embeddings, but we will probably need to change it. Okay, so let's just do we have embedding size here? Let's try to look at that. We don't have embedding size. We can have the embedding size different if we want. Then we would have here in features defined in the parameters actually, but we can keep everything the same size. So this will be the hidden size, then the queries keys values. So these will be our main parameters here. Then sorry, the middle feed forward model, middle part, and the middle part I will try to model the same way as I have on the equation on the, I don't think it was the third slide, or which slide it was. Try to find. Oh, okay, this is interesting. What did I do? Okay, I don't know. So this was the slide number 3, I think. Yeah, slide number 3. Okay, cool. Okay, so now like that. Okay, cool. So the middle part, there again, we will not change the sizes. You can change the sizes, but we can leave it as that. Actually, if you want, you can do something more interesting. We can, let's say, squeeze it a little bit. So if this divides by 2, which I think it does, yes, hidden size, yeah, 64, we can squeeze it and then make it larger again. And then relu. Then get it back to the same size. Any part in the middle part where there is, abstraction around the layers, it's very easy to change size. It's more difficult to change size here in the front part. We can do it by input parameters, but it's more difficult. Then finally, we need to these learnable normalizations. So this would be norm 1, torch and layer norm. And layer norm will go by the normalization shape of the hidden size again, and the other one will be the same. Okay, good. And this is actually very significant. What we are trying to do, we're trying to make that the model learns query key value behavior, but we are not we don't have data set that is specifically trained to achieve query key value behavior, but just because of our architecture, because we're making our architecture in a way that we have, let's say so how is our architecture? So architecture is made so that we have equation where we have this transpose matrix, we have multiplication by value. We are forcing the model to learn what we want just by architecture. Because the you can imagine that water flows through the right channels, like the gradient of the error flows to the right channels. This is also significant because the same way is applied in many different models. For example, in reinforcement learning, often when you have just reward value at the end, you don't have much control over what's happening. And the only way how you enforce your expert knowledge is by producing the equations in the model so that it achieves the best result. So that imagine like if you would be an expert and you would get the best key value, best query value, best value, you would use it in the way in this equation to get the desired result. If that makes sense. Maybe it doesn't make sense for you, but the more you work with these models, you kind of start seeing that you can force the behavior by architecture alone. So let me find. Okay, so this will go here. So I will give you some examples of code here, and then hopefully you can replicate this carefully. And then the homework, I will try to make something interesting as well. And then again, remember that there will be additional lecture which we will not hold in person, in online, but this will be recording on reinforcement learning. Please watch it so that you know that area of machine learning as well. And then you will be ready for exam. And if you want to continue researching these things, we will have another course in February, which is freely for you to join if you want. So, okay, so this is this part. Okay, so how we get key query value, query key value, what is the order? Yeah, query key value. So we get it by self query forward, and we feed in the same thing. And here it is a little bit misleading. The X is actually containing the positional embedding plus the word embedding. So this is what is the X actually. So this will be key, query key. So be careful not to use the wrong names here, because the model will work, but the results will be terrible. And this is common actually with these kind of models. There will be attention layer. Attention layer will be query times key transpose 1 by 2. And what I'm transposing here is so basically the output will be so let me give you the whole stuff here. So the query shape will be basically a batch sequence hidden, batch sequence hidden, then key transposed shape will be hidden sequence. And finally, the output shape, which is this attention matrix, attention shape will be batch every sentence, having the sequence by sequence. And this will be just two-dimensional matrix with attention values, basically. And then we need to do a couple of other operations. We need to normalize it. Again, this part I believe is not really needed. I still don't know exactly why this is left in the equations. Basically, this is kind of trying to make sure that that the scale is in the right limits. Okay, so that part. Then we need the softmax. Where is the softmax part? Okay, so but before the softmax, we need to mask the future. So masking the future looks like this. Mask the future, which and this means create me a matrix where there is the triangle, lower triangle, filled with values, and upper triangle empty, basically with zeros. So torch ones of the size of sequence size. We need to pass it to GPU. Every vector that we make in forward pass that is not predefined in self needs to be passed to GPU. So then attention mask, there will be attention mask fill. We can do these operations with for loops as well, but if we do that, then it will be slow. So everywhere where there is a mask of 0, which is the upper triangle, we want to put the value of float minus infinity. And why I'm doing this is because if I apply it now, right, this is correct, yes. So if I am applying now the softmax, what I will get actually is I will get that everywhere where it's minus infinity, there will be 100% 0. So it will never take those tokens. attention mask, dimension 1, -1. So we are masking the future here. Masking, oh shoot. Okay, masking future. And there is the attention for -infinity will be always 0. There is one more thing missing. Unfortunately, this is not as simple. We need also to mask the sentence lengths, because not every sentence is the same length, which also makes us a little bit of problems. This was the same problem for the RNNs, which we did not fully solve, but it is possible to solve for RNNs. It just takes quite a few lines in code, which is then difficult to do the live demo. So length till, so what I'm trying to do here is, so I'm trying now to go by the y-axis, and everything that is beyond the length of the sentence must also be float -infinity. And then also by the x-axis, all of the sentence tokens, like positions, after the length also should be -infinity. So it will make the mask matrix a little bit rigid. So it will not be as smooth triangle, but this is what we need to do. Okay, so what I'm gonna do, probably I will split this code, like put this in 2 parts in the whiteboard. This is the first part. And now the second part will be the easy part. So self-attention is done. After self-attention comes the easy part. Out attention by at value. Again, here is the tricky thing that, so let me see, attention, need to make sure that everything is in the right order. So attention goes by batch sequence, value goes by batch sequence value. I will reduce the sequences out, and I will get the correct two. So why I'm doing this, I'm just trying to show you, because one student had problem with matrix multiplications. So here is 2 dimensions. 2 dimensions, everything checks out. So I will remove this sequence dimension. I will get sequence by h, which is what I want. If there would not be the same dimensions, I need to then expand dimensions. So because otherwise I don't want to mix in the batch. So then out 1. Oh, here I want to show you one additional thing. I want to show you that often you could add dropouts as well, and dropouts is super powerful thing, because basically here I define predefined dropout, and this is only during the training, but you can also use dropouts in the inference mode. And what dropouts does in the language models is that every time when you run the model, you will get different output. It will feel more human-like. Also, dropout is basically temperature. If you add higher dropout, you will get more random outputs. If you get dropout to 0, you will always get the same outputs, which is important thing for you to know. So that will be that one. Then out 1 norm. So this will be from the self norm 1 forward out 1. Then goes the middle part. Out 2 is the self ff middle, forward out norm this one. Then we will skip it around. Out 3 is out 2 plus the skip connection. We always have these skip connections for the gradient, so we don't have vanishing gradient. Y prime will be self norm 2 forward forward out. If we want, we can add here also the skip connection, but we can leave it as that. So basically, that's about it for the self-attention transformer block model. Then we just need to put these transformer blocks in the layers sequence, and finally train the model. We also need to put actually the embeddings correctly there. Okay, so here is the model itself. We have the word embeddings, we have the positional embeddings already given how to do this so that we don't waste time on it. So let's just define it. Actually, I don't like that this is included in the template because this is also something to talk about and explain. Sorry, okay, so let's define those up there. So there will be self project project we. This is word embedding, torch and embedding, and this is the best if we train it from scratch because it will basically do this contextual locations in the hyperspace, but also actually so for you to know, the word embeddings are not only in transformer in these kind of architectures. I highly recommend also to look at word2vec models and glow models. They are still used in nowadays in combination with the GPT embeddings actually. So embedding dimension will be hidden size, so everything is the same size. Then the projections for the the positional embeddings. So these will be the positional embeddings, and these are predefined from positional encoding. These can also be learnable. I think one way how to do this best way would be to predefine them from this positional encoding, but then make them learnable. This is something to do, also possible to do. Okay, so this is that. Okay, then the transformers themselves, the layers. So layers will be torch and module. Unfortunately, module list because we have complex inputs and outputs. Transformer layer. If the inputs and outputs match, then we can use sequential in range of transformer layers. And finally, the logits self. All right, do we have, by the way, I didn't want to have FC at the end. Just a second, I think we don't need it. Definitely, we don't need it. Yes, let's forget about it. Because we have the transposed word embedding. Okay, so let's use this one. So this is that. Okay, and then this part. So we have word embeddings done with these packed sequences. So then we need to have so what is happening here, I'm just generating a line of indexes. So it's just giving 0, 1, 2, 3, and so on till the length of sentence. And now I'm making this to the positional embedding, basically. So, and we could actually pre-calculate these, but let's do it in this way. embedding, and now we're adding the dimension for the batch, and now we are copying the same pointer. Expand gives us the same pointer in the shape of unpacked size. So we are just filling the batch times the same thing. Okay, good. Then the x will be x so x embedding plus position. I mean the word plus positional will be the unpacked plus p. This also is unpacked actually. Good. Then these things we will pass into the basically, let's just write it out, the node into the layers. So for layer in self transformers, and let's say layers. So, and then here the output will be the first one, but then the attention matrix is something that we could just visualize actually. Forward, out, lengths, it's one. And finally, we need to just pack all of these things together. Just mean let's copy the packing. So this is the packing of these things back in the format what I wanted. Then, so this will be the not Y packed, but this will be out packed. Then finally, I want to have it out packed, flattened. This will be out packed data and logits basically. So logits now, and logits we will get from the transposed word embedding. So self project project word embedding, and wait, and here is a little bit of trick. Basically, this is actually transposed embedding by default already. So, and then I can do here out packed flat. I definitely need to add additional dimension here. And then after I need to remove that dimension. Great. And finally, we need to have y prim, just y prim as the softmax, torch softmax logits dim -1. Great. That's about it. So this is the full architecture basically of the very simple GPT type of GPT-2 architecture basically. Let me check if there's something else. The inference looks very different from the simple I mean the RNNs, because we need to feed in the whole sequence and then it will generate the next token. That's the way it works without memory. So that's about that. Okay, so we need to wrap up today. Please follow in the Moodle. I will post the reinforcement learning pre-recorded lecture. Then we will meet together on the exam in different locations. And if you want to keep learning these things, write me an email and I will add you to the course in February. So that's about it for our lectures so far. Okay, so thank you. Bye bye.